Hello, grade 12s. In this next lesson, we're going to look at rate expressions, and rate expressions will refer to um, the individual rates of each of the reactants and products and how they can compare to each other based on their stoichiometric coefficients. Right. So we um, alluded to that at the end of our last lesson, and now we're going to start to look at it in more detail. Okay, I should say that to make sure to clarify what will be coming very soon, lesson posted for Friday on rate law is that um, this this lesson, our rate expression, is again comparing reactants and products to products or reactants to products. So individual rates of change for each substance can be compared in this way. So let's get started. Um, pen here. Okay, so in this balanced equation, we have our lowercase a, b, c, and d. These are our balanced coefficients from this hypothetical reaction. These are found and can be equated to each other, to each other's rates of change in this way. So reactants will change their concentrations by decreasing. So we have a negative sign here, right? Negative sign there and there, right? And in our denominators, we find their coefficients, A and B. For our products C and D, we have the lowercase c and d, their coefficients in the same locations at the bottom and in our denominators, and our rates of change for each of those C and D found here. So rate of change of concentration of C over time, and same for the rest of them. Notice though, they don't have negative signs, they have positive signs. Right, so we can now compare any substance inside a balanced equation using the stoichiometric ratios in this way. Okay, let's get into an example. So in this reaction, we have hydrogen and iodine gas reacting to produce hydrogen iodide. Now, this is balanced, and our mole ratios are 1 to 1 to 2. So we can say that hydrogen iodide is being produced twice as fast as hydrogen or even iodine is being consumed. So we can write a rate expression that will compare hydrogen and hydrogen iodide reactant and product. They will look like this. Right? So 1 over A, which will be 1, just the number 1, so it'll be 1 over negative 1 over 1. The concentration rate of change in concentration over time, that would be rate of the consumption of hydrogen, is equal to 1 over 2 because of the coefficient in the balanced reaction of the rate of change of hydrogen iodide, change in concentration over time. Right, so that's essentially the comparison between these two substances and how we can set it up. So if we know one reactant or product rate of change, we can figure out the other one in this way because of this overall general relationship. Okay, real example. So here we have a reaction in a 1 to 3 to 2 reaction. Nitrogen, hydrogen in this famous reaction producing ammonia, and it's asking what is the rate of consumption of each of the reactants, so nitrogen and hydrogen here, if the rate of production of ammonia is fat. Okay, so we have this information. I'm going to flip back and forth because this has been my pen today has been lagging just a little bit. So I'm going to go back. I'm going to go to my blank page here, and it shouldn't lag as much. Okay, so in this example, it's asking us, and I'll go back and forth so you can see the question. It's asking us to compare nitrogen to, so rate of change. Let's figure out the rate of change of the concentration of nitrogen gas, right? Looks like this. Okay, and we have that, going back to the question, we know the rate of change of ammonia is 4 times 10 to the negative 3 moles per liter per second. So off to the side here, the rate of change of ammonia is 4.0 times 10 to the negative 3 moles per liter per second. Okay, and we need to figure this out. We don't know what that is, but we can write an expression that connects this reactant to product. Right, so in the balanced equation, we have a coefficient here of 1. So we can write this. Remember, it is a reactant, so it's going to be negative. Negative 1 over coefficient was 1. And then it's the rate of change of nitrogen gas, which is this, right? We want to solve for this entire thing equal to, right? Now that's going to be equal to the product, which is this, but the balance coefficient shows us that this is a 2, so that's what we're going to write. But this time, to emphasize that point, it's going to be positive because we're producing products, right? The concentration is increasing, not decreasing. So, ooh, jumped ahead there, thinking about the rate. That's given. All right, we have 1 over coefficient, which is 2, right? Then we have rate of change of ammonia. All right, and we're ready to start plugging things in and solving for our unknown. Our unknown in this case, let's highlight this part, our unknown is this, rate of change of nitrogen. Right, so we're going to solve for that. Okay, let's plug things in. So 1 over 2, 4.0 times 10 to the negative 3 moles per liter per second. This is really just negative, right? So negative, right? This negative sign goes over here. Well, you divide them, you divide this out. What you do to one side, you do to the other. So essentially, and we're going to solve for this as well. Our answer is now this. So the rate of change of nitrogen as a reactant is negative, right? Negative 2 times 10 to negative 3 moles per liter per second. Okay, and that's the answer to this. Next, we're going to do hydrogen. Let's see if I can scroll down a bit, give some more room. Okay, so same rate of change of ammonia, different setup for our for this expression because we have a different balanced. We have a different coefficient here. We have 3, so that means negative 1 over 3 rate of change of hydrogen is equal to, okay, positive here, same coefficient, it's still a 2, and we know that it's for ammonia. Okay, we know this value. Let's start plugging things in. All right, so 1 over 2. Okay, negative 1 over 3. We again want to solve for, it's asking us for the rate of change of the other reactant, hydrogen gas. Okay, so we want to solve for that. Right, I'm going to do this in hopefully a few less steps, but I'll go through what I'm doing. I'm going to simplify this. It's going to be 2 times 10 to negative 3 moles per liter per second, but I'm going to multiply that by negative 3 actually, to isolate for our unknown variable. And what we get at the end is a negative 6.0 times 10 to the negative 3 moles per liter per second, and that is the rate of change of our reactant hydrogen gas. And we're done. That is our final answer. Okay, so going back, this is your home fun. Give it a shot. Send me any questions. Hope this helps.